Now I'd like to show you how to perform a grid-based camera calibration. We'll print the grid target, take an image of the target and convert it to grayscale, and then evaluate the various distortion models available. I'm clicking the Windows Start button and then going to the National Instruments folder. Scroll down to Vision and then Documentation, and then finally NI Vision, and you will see the calibration grid PDF file. I'll open that up. Do File, Print, and this is the critical part right here. You want to make sure that you are printing at actual size. There can't be any scaling going on anywhere. After you've printed the dot grid, confirm that it is exactly 19 centimeters by 19 centimeters. I'm now in NI Vision Assistant, and I'm taking some images from my Microsoft LifeCam Studio webcam. This is with the dot grid that I printed recently. At this point I'm moving it around. The orientation is not super critical at this point, but it's nice to have the dots more or less lined up along the pixel rows and columns. It's important to make sure that the camera stays exactly the same between calibration and regular use. I encourage using manual focus and then recording that value for future use. Right, looking for image calibration. Let's go ahead and click on that step. You say New Calibration, and we are doing the distortion model. Go ahead and click Next on that. Next one more time. And when you see a picture like this, it's not so obvious, but this tells you things aren't working properly. The grid calibration only works with grayscale images. I'm going to cancel out of this step and then cancel one more time and look for the color plane extraction step located right here. Select that step and extract the luminance plane. Now we see that the image has gone to grayscale form. Now I can go back and find image calibration. Again, New Calibration. Selecting the distortion model, select the image, and let me look at the image in its entirety. And when you see that, it tells you that it has properly detected the dots, and that looks just fine. These are on 1 centimeter spacing. Let's go with 10 millimeters. That way my fundamental units for measurements will be based on millimeters. All right, looking at the top of this step 5 in the dialog box, we have distortion model selector, and you have 5 different models to choose from using this slider. I'm going to draw your attention to the percent distortion indicator. This is our primary metric for how well the model works. I'm getting about 0.26 right now. 0.24 is a little better. Notice that the option for correcting tangential distortion is selected there. 0.23. And finally 0.21. Tangential distortion means any misalignment between the sensor and the object plane, and so the tangential option is oftentimes useful. Now, error at the cursor, as you roam your cursor around the image, you can get a sense of how much error you're likely to have, and error tends to be higher out at the periphery of the image. This is typical of lens distortion. We have some other ways to evaluate the distortion model. This is a nice one, the combined error map. Again, it visualizes it here. We have lowest error in the central portion of the image, highest error out here in the corners. You can also take a look at the corrected image And this gives you a sense of how much the original image had to be warped in order to make the dot grid fall on a perfect, ideal dot grid, perfectly aligned in horizontal and vertical directions. In this last step, you can pick the origin of your coordinate system. It's automatically been picked as this upper left corner dot. I'll just go with that as the default. Finally, click OK, and you get a prompt to save the calibration file. I like to use today's date and some descriptive label to remind me how that calibration image was made. One last peek at preview corrected image. Again, if you look carefully, you can see where you've got some black edges there where the image has been warped a little bit to get the dots in perfect alignment. Let's try one last thing here. I'll measure a length between the dots. We know the dots are aligned on 1 centimeter centers, and that would be 10 millimeters. So I'll measure the distance between two left edges of adjacent dots. And we look down here and I see 10.04 millimeters. That's pretty close to 10 millimeters. Let's also try this where we know the error is highest, and that's in the corners of the image. Try measuring that same distance again. 9.97. This represents about 0.3 to 0.4% error, and that's pretty good.